Hello, students. We're going to be talking about reaction rate, and this would be sections 12.1 and 12.2 of your Zumdahl textbook. The PowerPoint is from McGraw-Hill Publishers. So we're going to be talking about the speed or rate of reaction. And so what we're going to be looking at, for the most part, are very simple reactions in chemistry. And we start off by looking at decomposition reactions. So if you recall, we identify decomposition reactions as one molecule decomposing into another one. And when we talk about the rate of a reaction, what we're looking at is the change in concentration per unit time. So why is this important in chemistry? It's kind of an interesting thing because we haven't addressed this before, so this topic is new. Some reactions occur very fast and some occur very slow. And if you think about, as a chemist, we would probably need to know that to take into account how to optimize a reaction. In terms of industrial chemistry, this would be very important. If you're making, let's say you were in charge of making a chemical, you would want to know if your reaction rate was going to be fast or slow and how to optimize yield. As a biochemist, this becomes a very critical discussion because in the body, when we process glucose and fats for energy, we need those reactions to occur quickly to keep our brain functioning and muscle contraction. And so reaction rate plays a critical role. In the case of biochemical reactions, those reactions tend to need help in speeding up and going faster. And so they involve biological catalysts, which are called enzymes. So that's kind of the kind of big picture of why it's important, why this topic is important. And so the first thing we're going to do is define rate, which is our speed of reaction. And the definition is that it'll be the concentration of, in this case, A, which is the reactant, over change in time. So I like to think of this in terms of a graph, and there's some prettier graphs to follow. This one's not so great, but there's concentration and here's time. If we start off, let's say, with a certain amount of A, over time, as the reaction, as it decomposes, it's going to decrease, right? And so A is going to get smaller. The amount will get less. All right. Now, if we think about the reaction, we could also think of it in terms of product, B. So initially you wouldn't have any, and then over time, you'd get more. So this is the idea that as the concentration changes over time, that's our rate of reaction. So to find the rate, and we're going to look at some numbers here more in a minute, we would take concentration at time 2 minus concentration of time at time 1 divided by time 2 minus time 1, and we'd get a certain value. Now, the way that we're going to be expressing rates is shown by this notation here that I am circling in the little cloud. The delta symbol will be our change. The brackets for A are concentration, which our favorite unit from Chem 200 was molarity. And if you recall, molarity is moles per liter. On the bottom part, again, change. And we have T for time. Time can be any unit of time, seconds, minutes, hours, days. The common one will be seconds. So, but just keep in mind, it can be any unit. So if we think about how we're going to express the rate in terms of units, it would be molarity seconds per second. And so we could also write that as capital M, seconds to the minus 1. And you should be comfortable with both types of notation for that. Okay, There's one thing also that maybe you've noticed here is this negative sign, in front of the change in concentration of A over change in time. Now let's go back to my not so great graph here. A is decreasing, right? So this top part here that I'm highlighting in the expression, this is going to be negative because it's going down in the amount. But the rates, we always want the rates to be a positive value. And so because of that, we are going to put this negative sign out in front to make the rate positive. One other thing to consider is that the rate doesn't have to be expressed just in terms of reactants. We could have also written the rate in terms of B forming. So that would be the change in concentration of B over change in time. Now, because the amount of B is increasing over time, we don't need the negative in front of the product, right? That's just going to stay as a positive. Here's another graph of what I just tried to show you on my graph that wasn't so nice looking. Here is C2H4 plus ozone, kind of a strange reaction, but it's not a decomposition, but what you should notice is that this graph is monitoring the concentration versus time, and the C2H4 is a reactant, so it's decreasing, the red graph. The oxygen is the product, so that amount is increasing. And so in this case, we can start to write what are called relative rates. The mole ratio is 1 to 1, right? C2H4 is disappearing at the same rate as oxygen is appearing. Okay, and so how would we write that? And I verbally said what's written here. The oxygen increases just as fast as the C2H4 decreases, and we can see that from the graph from the nice picture. Now, how would I go about writing that? Is since they are equal, the rate would equal negative change in C2H4 over change in time, because it's negative because it's a reactant, and that would equal the change in the oxygen over change in time. And this is then the mathematical expression for what's written verbally, is that the oxygen increases just as fast as the C2H4 decreases. Now, they're not the only species involved here. If you notice, there's the ozone. So here's O3, and then here's C2H4O. So we could have included those. Notice for the ozone, there's a negative in front because it's a reactant. And notice for the C2H4O, there's not a negative, but just plus, right? Positive, because it's a product. And all of these are equal in terms of their rates because of the 1-to-1 mole ratio. Oops, dropped my pen. Okay, so now let's put some numbers to this. And I really like this graph a lot. I know it has a lot going on. One of the things that I want to tell you is that reaction rates and this whole discussion of kinetics is very data driven. So we're going to be looking a lot at data. So our data kind of got squashed here down at the bottom. We have time and we have concentration. Okay, notice the concentration is essentially in molarity, right? Moles per liter. The time is in seconds. So let's take a look. Over time, the concentration of O3 is ozone. The concentration of ozone begins to go down, right? It's going to decrease. And that's expected because, as we see up here, our ozone is a reactant. Okay, on the graph, the concentration versus time as it's decreasing is the black slope, black graph here, the data. And that's showing that it started at 3.2 times 10 to the negative 5. And after 60 seconds, it ended up at 1.10 times 10 to the negative 5. So these data points are all reflected in the black colored graph. Okay. Now, we can talk about different types of rates. There is, first of all, what's called an average rate. There's what's called an instantaneous rate. And there's what's called an initial rate. Okay. Now, an average rate will depend on which interval of time we are assessing. So if we look here, the first one, and I'm going to just do a check, that's the average rate from 0 over the time interval of 0 to 60. And the average rate there is 3.50 times 10 to the negative 7. Now, where are they getting that number from? That's going to be rate will equal negative, because that's our reactant. And then we'll look at concentration to 1.10 times 10 to the negative 5 minus the initial, which was 3.20 times 10 to the negative 5 divided by our initial or final time is 60 minus 0 seconds. If you want to take a moment to plug that into your calculators, you can pause me and you can do that. And we should end up with 3.50 times 10 to the negative 7. Okay, now, if we want to take the average rate over a different interval of time, excuse me, in B, that would be 0 to 10 seconds. We would do the same calculation, but over that interval. So that one would look like rate equals negative 2.42 times 10 to the negative 5 minus 3.20 times 10 to the negative 5 divided by 10 minus 0. We should get the second number. Okay, so I think hopefully you're getting the point that the average rate will depend upon the interval of time that we're looking at. And it can vary depending on the time interval. Okay, all right. Now, there's this one here, D, point D, which is what's called the instantaneous rate. The instantaneous rate will be the rate exactly at time that we're specifying, which in this case was 35 seconds. Now that's a little bit different, right? Let's think about, let's say you're traveling in your car. You have an average speed that you travel from, let's say, your home to Mesa or Mesa back to your house. That doesn't mean that every single moment of time you're traveling at that speed. It's an average. Sometimes you're going really fast on the freeway. Sometimes you're slower, right? So what if someone asks, what rate or speed were you going at exactly one point on your drive? That may or may not be the average, right? So the same concept is here, that at 35 seconds, we want to know what's the speed of that reaction at that point I'm highlighting there with the big red dot. So for that, we have to go do a little bit more work, which is to draw the tangent line. You see that kind of tan colored line. So for instantaneous rate, I'm going to do a little star. You need to draw the tangent line to that point and find the slope. And that will give you the instantaneous rate at that particular time. There's another rate that's called the initial rate, and that would be the time at the initial point that you're starting the reaction. And once again, we would draw a tangent line, which would in this case be that purple tangent line E, and we would take the slope and we'd find the initial rate. Okay, now as far as reactions go, and what you're going to be doing in lab, usually what we do is it's in a reaction, we can find the initial rate a lot easier. So a lot of times our experimental procedure allows us to find the initial rate. So that's the importance of the initial rate versus other data points. Okay, let's talk about relative rates when we don't have a 1-to-1 mole ratio. So here's our reaction of H2 and I2 to form 2HI. Okay, so they are not 1-to-1. If you notice, we have 1 mole of hydrogen with 1 mole of iodine to make 2 moles of HI. And so hydrogen and iodine are disappearing at the same rate. Okay, those guys are disappearing at the same rate because it's a 1-to-1. But the 2 in front of the HI tells us that HI is appearing twice as fast as H2 is decreasing and I2 is decreasing. So here's the words that I just said written. HI increases twice as fast as H2 decreases. And you can see from the graph, this graph looks a little shifted from the previous ones that were 1-to-1. HI goes up twice as fast as H2 decreases. Now, if we were to write this out, we could write it like this. HI, the rate of HI, because that's our notation, change in HI over delta T, is increasing twice the rate that I2 disappears and twice the rate that hydrogen disappears. So that is true, and that's based verbally on what I said. Now, if you look closely at this expression that I've written out, we can also write it a different way. And I should probably include the negatives in front of the reactants, right? Okay, so we can also write it a different way. Notice if I want to talk about the I2 disappearing and the H2 disappearing, their rates are 1/2 of HI. So think of it this way, that I would take the 2 that I'm going to check here and divide it to the other side. So what I come up with is this expression here. Okay, and so this is an OR. I started off with this first top one where HI appears twice as fast as H2 and I2 disappear. Or we could say that I2 and H2 disappear at 1/2 the rate of HI. Now I'm highlighting, and I'm going to put the first route as a highlight because this is going to be the standard for how we write relative rates. So this will be a standard way of writing relative rates. Okay, now why did they pick that as the standard versus the other one? I think they're just trying to make things easy. And so let's take a look what I mean by that on the next slide. That if we have a reaction, just a general reaction of A plus B plus going to C and D, that we just pull the coefficients down in a fraction, and then those give us our relative rate. So we don't have to think so much about who's going at what rate compared to the other one. So in this case, then, rate would equal negative for the A, 1 over A, change in A over delta T. For B, I'll pull it down. For the C, we pull down that coefficient, but I don't use the negative because it's a product. And then for the D. Okay, so this is how we're going to treat what are called relative rates. Now let's practice this on our actual equation. So hydrogen gas has a non-polluting combustion product, water vapor. It's used as a fuel aboard the space shuttle and earthbound cars with prototype engines. So there's 2H2 gas plus O2 to make 2 water gas. So we're going to express the rate in terms of changes in H2, O2, and water with time. And when O2 is decreasing at 0.23 molarity seconds, what is the rate at which water is increasing? So you can pause me right now and then try the problem. And then I will go through it with you. So you can pause me. Okay, so what we would do is we'd say rate equals negative 1/2 change in hydrogen over change in time, which equals negative 1/2 change in oxygen over change, oops, not 1/2, sorry. Oops, I did not mean to press that. Here's my eraser. Okay, so no 1/2 on the O2, right? Okay, and then for the water, now I have a 1/2 change in water over change in time. Okay, so now we're going to essentially substitute, right? When O2 is decreasing at 0.23 molarity over seconds, so this is our rate for the oxygen. That is this number there. And now we want to solve for the water. So what I like to do is to simplify this and make it just a little easier to deal with. So the change in oxygen over change in time is 0.23, and I prefer molarity seconds to the -1 versus writing out the whole unit like that. And then that would equal 1/2 X. And I'm going to call the water that we're trying to find X. So X equals 0.46. So let's think about if that would be true about what we said. We said water is going to appear twice as fast as the oxygen disappears. And is that true? Yes, 0.46 is twice as much or fast as 0.23. One last thing, if you notice, I ignored the negative. The negative's really telling us that it's like formally saying that that's a reactant. Rates are always positive. So I'm going to keep that rate as a positive value. Okay. Okay, and here's the solution if you want to see it as a prettier PowerPoint than my writing. Okay. Okay, so that was relative rates and understanding what rates mean. The whole focus of the chapter is to expand upon that and determine for a reaction what is known as the rate law. The rate law tells us a couple of things. Primarily, it's going to tell us what the dependency is of the rate on concentration. So I'm going to write that up here. It's going to tell us how the rate changes with concentration. The other important thing it's going to tell us is it's going to give us a proportionality constant called K, which is the rate constant. Now, let's take a look at how the rate law will be written out. Rate will equal the rate constant K, that's our rate constant, times the concentration, in this case of A. And then you see the M there, that is what's called, M is called a reaction order. That's going to give us the dependency of the rate, how it changes with concentration. We're going to talk more about M and N in a moment. In times B, the other reactant, times its, or to its order, which is essentially, the dependency is the superscript there. It's an exponent. So M and N are exponents. Okay, we're going to expand on that in a moment. Couple things before we move to focus on M and N for right now. If we notice, the rate constant is the proportionality constant here. But one thing is very clear is that the greater the K is, the bigger its value, the faster that reaction is going to go. And then the question is going to be, what determines K? And that's a whole other section of the text in terms of, I think it's, don't quote me, 12.5, somewhere in there. Okay, so we're going to get to that. Okay, now M and N are exponents. Common orders for M and N are 0, 1, 2. We're going to come back to that in just a moment. But the most important thing for right now is to understand that this is the goal of the chapter, is to figure out what the rate law is for certain data. What is the rate dependent on in terms of concentration, and how? Okay, what are these exponents that are going to determine how the rate changes with changes in concentration? The other important part is we cannot eyeball a reaction and figure out what the reaction orders are. This comes from experimental data. So that's why this is highlighted, bolded, that M and N are determined by experimental data. There are going to be two types of data that we're going to learn about. One is going to be what's called methods of initial rate. And the second is going to be integrated rate law. So the next PowerPoint is going to be talking about methods of initial rate. And then the third PowerPoint is going to be on integrated rate law. Okay. All right. One other thing, our rate constant. Later, we're going to see that the little k here, cursive k, is temperature dependent. And so we will talk about, there's an equation that describes that dependency, and we'll get to eventually. Okay, so let's talk about what orders mean, and then we will stop here after this to give you a chance to kind of think about what I've gone over. An individual order is described in terms of an exponent. So, for example, we would collect data. And if the rate doubles when A doubles, the rate is said to be first order. So let's think about that. If rate equals K, A to the 1, it's a really bad looking one there. Okay, if rate equals K times A to the 1, notice if we doubled A, 2 to the 1 is 2, right? Yeah, 2A. Then 2 to the 1 equals 2. And so the rate will double. So we will need data for this, right? We would need to see how the rate changes if we changed A in a decomposition. And if we double A and the rate doubles, then we conclude that the reaction is first order. First order will simply mean that this exponent is 1. Okay, now the M and N business, if this is a simple decomposition, when we write it out, we would just call that M, an unknown order. YM, YN, I don't know, but it's just a generic term for the order that it is. Okay, now, based on our data, if the rate is equal to K, A squared, or second order, then if A doubles, what is 2 squared? 4. So the rate will quadruple when A doubles if it's second order. Okay, so that's a common order as well, or common scenario, that if we double the concentration, the rate goes up 4 times, then it would be said to be second order. Lastly, another scenario could happen is that the reaction is 0 order. Now let's think about what that would mean, that if A doubles, 2 to the 0 is 1, right? So what would happen is the rate would be unchanged. So if the rate does not change when A doubles, the reaction is 0 order. Now in chemistry, these are common orders. A lot of reactions are first order, second order, and 0 order. To give you sort of an impression of where we might see first order, we see that with the decomposition of radioactive atoms. They are first order kinetics. So like uranium or plutonium, they decay with first order kinetics. At the end of the semester, we'll actually apply this to radioactive chemistry. So that's an example, okay, of when the reaction rate is first order. Other reactions are second order. Some can be zero order. A lot of the zero order ones involve something special happening. So, like, for example, if you have an enzyme, that's my terrible picture of an enzyme, biological catalyst. Here's our reactant for that. Here's what's interesting about enzymes is if we look at their graph of what happens with their speed versus concentration of reactant, their graph looks like this. And what it's showing us is that initially, do you see the initial part here? That's pretty linear, right? So that as we add a reactant to that enzyme, it's first order kinetics. The concentration doubles, the enzyme can go twice as fast. So that's first order. But if we keep adding reactant, notice this top part, the speed plateaus. And what's that showing? That means that you can keep adding reactant, but the speed of reaction doesn't change. So this is a really neat example of a process that starts off first order, but then if you keep adding more reactant, ultimately it plateaus to zero order. You don't change the speed by adding more stuff. And that most likely has to do with the fact that at some point your enzyme is full and saturated. Okay, it can't keep going faster because it's already maxed out. Okay, so what we're going to do is we're going to learn the approaches with data to determine what order a reaction is. Is it first order, second order, or zero order? So that's where we're headed with this. The other thing I should say at this point is that these are common orders. This is where we start our discussion in kinetics. There can be other types of orders that are more unusual. So I just want to talk about those for 1 second, just to make sure that you're understanding what the exponent business is. You can have fractional orders. So take your calculator right now and picture that you're doubling A. So that would be taking 2 to the 1/2. So you have your exponent key. So take 2 to the 0.5 and see what you get. 1.14. Oh, sorry. 1.414. So what does this mean when it's the reaction order is a half? Is that if you double A, the rate goes up 1.414 times. Okay, so keep in mind, these are just exponents. They're the dependency, how the rate's going to change when you change the concentration of the reactant in this case. Okay, so that one's just not as neat and pretty as these other ones, right? We have to use our calculator to figure it out. You can have negative orders, uncommon, but can happen. If you have a negative order, what that means is something unusual is going on. And what that would mean is if you doubled the concentration of A, the rate would decrease by 1/2, right? Because 2 to the negative 1. So those are unusual, but I just want you to be aware that when we talk about zero, first, and second order, They are common reaction orders. Okay. One last thing is that this whole idea of doubling is fine, but hopefully you can understand, since they're just exponents, doubling makes it easy, but it doesn't always have to double. So in other words, if we decide in an experiment to triple the concentration of A, and if it's first order, then we should be fine to understand that if we're tripling the concentration and it's first order, the rate will increase 3 times. Right? We don't have to always double things. Okay. If the reaction is second order and we triple it, if we triple A, what do you think happens to the rate? The reaction will increase in speed by 3 squared, which is 9. Okay, so just make sure you're understanding that they're exponents and not, I know it's kind of hard at first to understand this, but they are at the end of the day just exponents, and we're just talking about them in a fancier way. So instead of saying that the exponent is 1, we call it first order. Instead of saying the exponent's 2, we call it second order. Okay, and that you should be able, once we start looking at data, don't get so attached to the doubling business, because things can change by other factors than just 2. Okay, here's a graph that shows the rate versus concentration. So this was kind of what I drew with the enzyme one, but separated out. So notice what's here for 0 order. If we double the concentration of A for 0 order, the rate doesn't change at all, so you have that flat line. If it's first order, if we double A, the rate doubles, so you get a linear relationship. For second order, if you double A, the rate goes up by 4, and so you get more of a curve. Okay, so that's a graphical representation of how the rate is changing with concentration for each of the 3 common orders. Okay, in terms of the rate law and order, I just want you to know the language. So let's take a look at this rate law here. A little bit fancier. The rate law is equal to rate equals K, the rate constant, times NO squared H2 to the 1. Okay, now how I would say that to somebody is, I wouldn't say it the way I just did. I would say that it's second order with respect to NO, and it's first order with respect to H2. Okay, so overall, the reaction is third order. Now let's think about it. They're both exponents, right? And when we multiply exponents, so when you multiply exponents, multiplying them is the same thing as adding them. So if this is a 1 for the H2, then that's why overall it's third order. Okay, we cannot look at a balanced equation and determine those numbers. We have to have data, and we're going to talk about the 2 major ways that we figure out what the orders are. Before we do that, and before we move on, I just want you to do and to think about one other important thing here. Is how the overall order affects the overall rate, the changes in the rate. So for example, if we double NO and triple H2 concentrations, what happens to our rate? By how many times will it increase? So take a moment to think about that. If we double NO and we triple H2, okay, so you can pause me to think about it. But let's now look at that. If NO is doubled, that would be 2 squared for the NO. And if the H2 is tripled, that's 3 to the 1. So how is that going to change? 2 squared is 4 times 3 to the 1, which is 3. So 4 times 3 is 12. So the rate will increase 12 times. 12 times K, essentially. Okay, so 12 times. Okay, so we're just treating the orders as exponents with, they're just exponents, okay?